As was already said, my name is José Pagán Munoz. Mouthful. Ethan, do I still have time to do the talk? Just kidding. I'm from CU Boulder. I'm a third-year grad student. And today, as was already said, I'm going to do my talk on charging and mobilization of dust particles in a plasma space environment sitting on a solid surface. Joseph's talk actually is a great sort of introduction to what I'm going to discuss, but let's get to it. So first off, I do kind of want to talk about the importance of understanding or the importance of the lunar dust and how it's being transported on the lunar surface. So you've probably all seen this, the surveyor observations of what is hypothesized to be the reason for the lunar horizon glow. So dust particles around 10 micron diameters being observed to reach heights of 30 centimeters. And on the bottom left, that's Eugene Cernan's sketches of a dust plume as they reach the termination line during orbit. And it was also seen to be approximately 0.1 microns to 1 micron dust sizes, reaching as high up as 10 kilometers. And that's all from the surface. That's understanding of how this dust is moving around, but we don't really fully have the full picture. So let's delve into the reasons why this is important as well for both on the right, as you see a spacesuit, so that's Jack Schmidt being covered, caked in lunar dust during their EVAs. And then on the left, that's the lunar dust detector measuring accumulation of dust, but hopefully to keep you all entertained is a nice little video in the center showing JSC1 lofting off of actual real spacesuit fabric. So that is using an E-beam. This is very interesting and important because we want to understand how does dust charge get onto solar panels, spacesuits, surface exploration systems, and possibly find some dust mitigating strategies once we understand the dust charging and the mobilization of that dust. So as was already just shown by Joseph, thank you, Joseph, again, we have this patch charge model by Shulong, my advisor. And we have these patches, the blue patches showing exposure to electrons, UV, and generating these secondaries. These secondaries will prove to be an important aspect of this model as they charge up those red patches inside the microcavities that we're calling the spaces between the dust particles, and cause Coulomb repulsion once they accumulate enough charge. And they will overcome any of the opposing forces that's keeping it stationary and cause lofting, as you can see in the top right there. Now, moving on to the current work. So this is PCM-SP. So this is extending this idea of the patch charge model to just a single surface, dust particles just resting on a solid surface. So this is where you get into dealing with the solar panels, getting dust onto the spacesuits, trying to understand also when it goes from a pile to a monolayered dust. So it's sitting on a dielectric surface, very similar to the original patch charge model, is you have those red patches that will be exposed to your UV or electron beam, and they generate secondaries. So they're generating those secondaries and going into those, being absorbed and depositing onto those blue patches or those corners of that jagged dust, and will do something similar. They will accumulate a charge. They can accumulate a lot of charge and cause this repulsion or this Coulomb repulsion. And one thing that we do is modeling with help from modeling from our collaborators. In this top right figure, we have a model of the surface charging of this dust. So a spherical dust, you could see the red patches on the top, colors with the patch charge model SP on the left. So we see these red surface charging on the top right of this red patch being more positive. And then on the bottom, these blue patches that are showing the depositing of these charges, these secondaries, in between the dust and the surface substrate. And one thing is to understand is, well, let's see how this actually affects mobility. Now, here's a nice little video. So we see two particles being tracked that are lofting as high as 5 millimeters and somewhere between 3 and 4 millimeters. on this dielectric substrate. And let me just add this little figure as well. So if you pay attention to this video, you see also these little dusts that are hopping. In that still image, we originally saw these from a 60 frame per second camera, that these dusts were being a little bit stretched. We were trying to understand their motions, moved on to the high-speed camera, and can actually see these little hops as well as these lofted dusts. So moving on to the actual meat of this, the results here. So just let me set this up real quick. We have three lines on this graph so far. So the first one is going to be the black line. This is the experimental result of mobility on Kapton. That was the substrate. So dust resting on Kapton. Then we have the blue line, which is the Coulomb repulsive force. This is modeled as well. And the red line, this is with the band. This is the secondary electron yield of Kapton. And they all sort of add up and line up perfectly on this peak. I could show with this laser pointer real quick right here. So right around 130 eV, we see a peak in mobility of the dust. We see a peak in the Coulomb repulsive force right at the peak of the secondary electron yield. This, what we conclude from this is that, yes, the secondaries play a huge role in generating, in causing mobility and lofting of dust particles, as also Joseph mentioned. And the Coulomb repulsive force peaks right at the same peak, which further validates this idea that these secondaries are causing this Coulomb repulsive force to overcome the rest of the forces, the downward forces, the negative forces are causing it to be static, to generate lofted particles, or to create lofting of these particles. And moving forward here, another thing, as Joseph even mentioned as well, is the UV exposure. So one thing is, yes, we saw UV mobility before. Here's an actual image that we did for this work, where on the left is the before, the right is the after, and you follow the color-coded dust particles, you see that they did move slightly. It's very slight movements, but it was very good for further verifying the model of PCMSP and the importance of generation of secondaries to cause mobility in this dust. So just to discuss some future work here is, well, here's pretty much three broad points. One thing I do want to mention is we want to look at different dust sizes. So right now we're currently working under 45 micron diameter dust sizes, looking to get even below into the sub-micron range. I had some great talks with a lot of people here, a lot of people that are really doing some of this work already. That I had some great talks. And if you also see anything here that you think you want to collaborate or want to mention or just talk about, discuss some of these that you think you might have like a cool plan around it or cool experiments that could aid in this work as well, I'll have my contacts at the end, and you can always talk to me if you see me around. So another thing is the lofting characteristics and shape effects, as Kayla even mentioned, which was also a great talk, discussing the shape effects, the particle shape, and microporosity. I think that's really interesting talk, and we're definitely going to talk a little bit. And then finally, as Joseph also mentioned, how many times did I say that? Charge mechanisms that may either increase or mitigate dust mobility. As was said, charge pumping could be one of these avenues where it increases dust mobility. And there might be even some other mechanism that can mitigate this dust mobility. That is one of the things that we're working on now, though. And so hopefully I can show that. But I like to end it here with thank you, everybody. And yeah, my contact's there. Please contact me if you have any questions or you want to discuss some more.
Thank you, Jose. Since we are a bit ahead on time, we have another 2 minutes right now. I'd like to just ask you a question, take the chair's prerogative here. So I noticed some really interesting, really cool research, by the way. So I noticed some interesting things about the charged particles that are lofting up, and I can see that you're trying to estimate or measure the charges. I'm wondering about the kinematics of the parabola that it's creating in your view. And like, can you estimate the mass of the particle either empirically or from the camera data and obtain charge or the force that lofts it and vice versa?
Uh, yes, actually. So one of the main things for this video is to estimate the launch velocities. And from there, we can get the potentials. And it's a parabola, and you can get from the heights here. You can get a lot of stuff here, including like you mentioned the mass. But this is still preliminary results. We are working on uh, making a more, I guess, robust program to get all of this information quickly, because there are a lot of videos like this. But yes, there's a couple of things that we're doing for future work that we are extrapolating from these parabolas and these trajectories.
Very interesting. Yes, because it strikes me you could use possibly spherical particles where you have a measured known radius and mass as a baseline to determine that, and then feed that forward into the actual irregular grains.
Oh, you're actually, yes, completely right, because we are also dealing with microspheres. We are already dealing with these particle shape effects and understanding the particle shape for this research. So don't
Okay.
worry, not you.
Okay, excellent. Thank you. Very interesting.